Hello everybody. So let us continue today our discussion further on the concept of nucleation and growth, and today we will be discussing about the qualitative understanding of the crystal nucleation model. And we have discussed in the last class that the formation of the pre-nucleation aggregates, that means there are certain small number of nuclei which are formed, and now these nuclei have to grow further so that they can form the final crystal. We looked at the classical nucleation pathways, and we also looked at the non-classical nucleation pathways, that is the one-step model and the two-step model respectively. And we also looked at a case study of olanzapine, where we saw how the different dihydrates or polymers can form depending upon whether you have the crystallization of these dense droplets on the surface or you dissolve these droplets further in the bulk solution and then crystallize out the new phase. In order to understand the process of nucleation, we realized that there are two important terms. One is the Gibbs free energy term associated with the volume change in the bulk crystalline material, and the second is the interfacial energy, where the energy has to be spent in order to create the necessary surface for the creation of the crystal. So we now have to look at both these processes, and it is the cumulative combination of both these processes that decides the overall drives the overall process of crystallization. So here we define two quantities, delta Gv, that is the Gibbs free energy of the nucleus per unit volume, and we define delta Ga, which is the surface free energy per unit area of the nucleus. And here we would like to look at this curve here. So we have delta G as a function of R, and this process of nucleation involves a certain activation barrier, and once you cross this barrier, then the process of growth takes place in a facile way. So here there are different regions we need to consider. So there is an activation barrier, and when you reach this activation barrier, this represents Rc. This is the critical size of the nuclei. At this particular point, delta G is equal to 0, and at R, so we call this Rd. So at R greater than Rd, delta G0 becomes less than 0. At R equal to Rd, delta G is equal to 0, and at R less than Rd, delta G0 for the process is greater than 0. So to start with, there is because the creation of the surfaces needs energy, this is the term which is associated with delta Ga, and there is a volume term which is associated with delta Gv, and it is actually a combination of both these processes that drives the overall process of nucleation and growth. And as we know that the formation of the nuclei is essentially critical, it is only after it reaches the critical size Rc that the Gibbs free energy change delta G starts decreasing. So the Gibbs free energy change start decreasing in this region, it goes to 0, and then it becomes negative. And therefore it is important to consider the size of the nuclei present in all these regions. So as I told you, initially there is a energy penalty because you have to create the surface. but there are also concentration fluctuations and thermal fluctuations. So at regions between R and Rc, the nuclei which are formed can also redissolve back into the solution because there is no barrier associated with the process. And that is the reason why when you do the process of crystallization, we have to keep them steady and not disturb the crystallization vials, because the nuclei which are forming in solution will again then rapidly redissolve back into the bulk medium, because you are giving the necessary thermal agitation. So on giving thermal agitation to the molecules or disturbing or giving or providing vibrations, then these nuclei again tend to dissolve back into the solution. So it is very important that we leave the crystallizations undisturbed for a sufficiently long period of time, so that we get the right size of nuclei, and then this nuclei can grow and give you the bulk crystal. Now it is also it was initially thought that we must, for the nucleation to proceed satisfactorily, because if nucleation proceeds satisfactorily, then only the growth process starts, because you have these critical size of the nuclei which is reached, and now they can start growing larger and create the crystal surfaces. More and more of these nuclei will be formed and they will attach themselves to the crystal surface. Now in this case, you see that whenever the nuclei wants to go and attach itself to the crystal surface, it is the Gibbs energy change is more negative because of the volume change due to the formation of the bulk crystalline material, but is also a resistance because you have to create the surface. So when you have actually crossed this barrier and the volume change is more, then the system does not respond to the negatively to the requirement of creation of surfaces. So you have a competition between volume change and surface change, and it so happens that the volume change dominates the positive energy necessary to create the surfaces. And so initially it was thought that delta G should be less than 0, but that is not the case. If you look at the region between Rc and Rd, so if you take say any particular radius, say Rx here, if you take Rx here, you will see that the nuclei which are formed are thermodynamically unstable, but kinetically they are stable. Kinetically they are stable. Why? Because if they have to dissolve, the nuclei in this region, if they have to dissolve, then they will face an increase in activation energy. So now there is a barrier. So you have this delta Gx, and this is delta Gc. So now there is a barrier, delta Gc minus delta Gx, and this is greater than 0. Because of this barrier, these will not be able to now dissolve back. So once you have crossed, that is why this distance Rc is considered to be the critical size, beyond which the nucleation proceeds further, and as more and more nucleation happens and you cross delta G less than 0, then the volume term takes over in a substantial way. So although this nuclei is unstable thermodynamically, it is stable kinetically, and therefore we are able to achieve the process of nucleation in a facile way, and the tendency to go back into the solution does not exist because the relatively large activation barrier depending upon where you are. So if you are in this region, say for example, then the activation varies so much, and as you go more and more higher in R, the ability to dissolve back becomes less and less feasible. So now we can look at a quantity which we can now compute the maxima of these thermodynamic quantities. That means we can now compute what is delta Gc, because that is the barrier height, and to do that we will have to first see the terms which are involved in this process. So in order to compute the barrier height, we will first look at delta G nucleation as a function of R. We can write here nucleation N. That is a combination of two terms. We have the volume phase into, that is the Gibbs free energy of the nucleus per unit volume. So this is delta Gv, and this is negative because it is associated with decreasing delta G, and the positive term is the 4 pi r square delta Ga, which is the surface free energy per unit area of the nucleus. And now to get the position of the maxima, we will have to take the first derivative of delta G and R with respect to R, and that will give you minus 4 pi r square into delta GV plus 8 pi r delta GA, and this is then put equal to 0, and from here we can get that 4 pi r square delta GV is equal to 8 pi r delta GA. So r cancels, and this gives me the critical radius, because now it is at r equal to RC. So now RC becomes, this is 2 delta GA by delta GV. So now you see this is the how you get the magnitude of RC, that is, it is the ratio of twice delta GA by delta GV. So the area term contribution, the free energy surface area is more important compared to the volume term. The ratio of this decides RC, and if you now put this value of RC into the original expression, then you will get the quantity which is called the Gibbs critical excess energy. This is the excess energy, that is delta GC, which will come out to be 16 by 3 pi delta GA cube by delta GV square. So this is equation number 2, this is equation number 1. So we see now that the barrier, the activation barrier, depends upon the cube of delta GA, and it is inversely proportional to the square of delta GV, and overall these decide the magnitude of the barrier height or the activation barrier which is required for the process. So once the nucleus has become sufficiently large in size, then there is a decrease in the free energy associated with the formation of the bulk crystalline material, and the interfacial energy does not become very significant now. And we also keep in mind that now the concentration fluctuations are also there that aid in the process of crystallization once you have exceeded the crystal size. And as we have realized in the previous lecture that there is a metastable zone, and we have to cross this metastable zone and go into the labile zone. So in the labile zone, the process of crystallization takes place, because now you have increased the levels of supersaturation, and then crystallization proceeds in a facile way. So if you want to enhance the nucleation and growth, you need to increase the supersaturation of the system, and increasing the supersaturation of the system will now this will now decrease the activation barrier. This will now decrease the activation barrier, and when the activation barrier now decreases, you need lower magnitude of RC to achieve nucleation. Okay. So you can actually now modulate or control the barrier height by increasing the supersaturation in the system, and that will also lead to more concentration fluctuations, which will statistically increase the probability of formation of more crystalline material at the expense of the energy necessary to create the additional surfaces. So now you see that as the activation energy and the critical size decrease, this process leads to spontaneous and rapid nucleation, because now you are increasing the concentration of these critical nuclei. The pre-nucleation clusters are increasing, and this can lead to now facile growth. So overall we see that this is the very basic concept of nucleation and growth mechanism in crystals. So this also accounts for the fact that when you also have a phase transition process, say one polymorph converting into the other, there it can proceed by the nucleation and growth mechanism, where the structure of the daughter phase is related to the structure of that of the mother phase, and the process happens gradually over as a function of temperature. And then there are some processes which happen due to dramatic changes in the structure, and the two polymorphs cannot be related to each other in terms of mapping the trajectory as to how one form converted into the other. And keeping this in mind, we now realize that the solution phase is actually the pathway to formation of polymers. And we have just now realized that just like in a chemical reaction, the reactant concentration is very important. In the formation of polymers, the nature and the concentration and the role of the nuclei is extremely important. So we can consider now a solution phase where we have this nuclei. In this nuclei, we have these molecules which interact via intermolecular interactions. They interact by intermolecular interactions, and they form a high energy dense phase, which is the nuclei. And depending upon the barrier to crystallization, whether the barrier is small or the barrier is large, depending on its barrier, we can have different kind of polymers which can form. So in this case, if the barrier is less, that means the activation energy is low, then we have got a kinetic crystal, and we call this delta G kinetic, and this is the change compared to that of the parent phase or the solution phase from which the crystallization takes place. So this is the delta G kinetic, whereas you can have a much higher barrier, which is delta G thermodynamic, and this will lead to the formation of the thermodynamic crystal. That is, this will lead to the formation of thermodynamic crystal. So just like you have kinetic products and thermodynamic products which come out from solution in an organic reaction, organic transformation, you can now have different polymers crystallizing out from the solution phase depending upon the structure of the nuclei and the changes happening in these nuclei, which actually lead to crystallization of the kinetic crystal or the thermodynamic crystal, and depending on the conditions which you give for crystallization. If you give very fast evaporation rates and high temperatures, then the tendency to get a kinetic crystal is high. But if you allow the system to equilibrate with the surroundings and you gradually lower the temperature of the system very slowly, you really reduce the rates of evaporation significantly, then statistically you are promoting thermodynamic conditions of crystallization. So the barrier can be higher, but it will give you the thermodynamic crystal, and once the thermodynamic polymorph is formed, it will not convert into the kinetic polymorph. And in this regard, what has been proposed, that when you get a kinetic crystal, it is actually there is now a competition between the maximization there is now a competition between the maximization of hydrogen bonds versus close packing, and it is the competition between these two sets of forces that decides the outcome of crystallization. So when close packing principles govern, this is in accordance with the rules of close packing as said by A. Kitogorowski, that you will have more weak interactions, but close packing will prevail, where you will essentially try to minimize the void space in the crystal and you will get a highly dense solid. Whereas if you want to have formation of supramolecular synthons which maximize highly directional and short hydrogen bonds, then the tendency to form a kinetic crystal is greater. And once this hydrogen bonds array is formed in solution, again these are quite stable, and it is very difficult to disrupt this hydrogen bonding structure and convert it back into the monomers, from where it can possibly go into the thermodynamic form where the close packing principles operate. So it is the competition between this maximization of hydrogen bonds and close packing which actually leads to kinetic and thermodynamic polymers. And also there is one very important assumption of classical nucleation theory, is that the arrangement of the molecules in the bulk crystal is very similar to that in the nuclei. Okay, and in other words, that whatever is the surface free energy of the nuclei in the of the molecule in the nucleus is the same as that of the bulk crystal. Now this is a very limited approach, because there are a lot of variations happening in the nuclei, and so assuming that the surface free energy of the nuclei of the molecules in the nucleus is the same as that in the crystal is an oversimplification, because now what can take place is that the kinetic crystal can actually convert into a neighboring phase which is having lower activation energy, then it can convert into another phase, and then it can finally convert into the thermodynamic phase. So during the process of crystallization, it is not that only the kinetic phase and the thermodynamic phase are these are the ideal conceptualization, but a kinetic crystal can convert into a thermodynamic crystal via sampling of the low energy minima. So these are the relatively lower energy minima before it converts into the thermodynamic crystal. And so in that case, the assumption that the free energy of the molecules in the nuclei and that in the crystal phase which is crystallizing out is the same does not hold good, and this process of conversion from one form to the immediate form which exists in a lower kinetic minima is referred to as the Ostwald's rule of stages. So we have got this Ostwald rule of stages, where the sample actually, or the crystal the nuclei actually explores a slightly lower energy minima, and then it converts into the next lower energy minima and finally transforms into the thermodynamic crystal. And this is referred to as a series of continuous crystallization processes, each process mediating the formation of a new phase with a slightly lower free energy minima compared to the one from where it initiated, eventually converting into the thermodynamic crystal. And this thing is also very common when you take a kinetic crystal and dissolve it in solution, and you actually stir this mixture for a period of 2 to 3 days. The possibility of converting into the other polymorph is very high. Now that is, you can access the neighboring polymorph. It can be another kinetic polymorph, and if you do this stirring for a long period of time very slowly, you might end up converting into the thermodynamic crystal as well. So all these processes talk about the relevance of nucleation and growth. Now what we will discuss further, let us now discuss further about the fact that now you have got polymers, you have got different crystalline phases, and now we would like to understand the concept of whether in solids one form can convert into the other, and this happens due to the existence of the phenomenon of phase transitions. So we have looked at nucleation and growth mechanisms, we have looked at polymers, but now we would like to understand the thermodynamic relationship between the polymers, and we would like to understand the concept of phase transitions, where one structure converts into the other, and this process of conversion of one structure into the other proceeds by different mechanisms. Two very common mechanisms are there. For example, there is a nucleation and growth mechanism, where the new phase is formed at the expense of the parent phase slowly, stepwise, and then there is a process called displacive transition or martensitic transition, where one phase converts into the other without any association of any activation barrier. Okay, so what is a phase transition? The phase transition is the process of transformation of a substance from one phase to another. And obviously we are only considering structural changes here, and the two most important variables are the pressure and temperature. And as I mentioned to start with, there are two types of phase transition. So I can write this as PT, which is different from pressure and temperature. Two types of phase transition. Number one, we have got nucleation and growth model, and this is slow, and the nucleation step is the rate controlling step or the rate determining step, and is a difficult and slow step. Whereas on the other hand, you can also have martensitic and displacive phase transitions, where these processes takes place via a diffusionless pathway. The activation barrier is very low, occurs spontaneously, and proceed at a fast rate. So, you have slow processes, you have very fast processes. The martensitic and displacive phase transitions are relatively fast, whereas the nucleation and the growth model is relatively slow. And then what was also proposed that time by a famous scientist called Berger, that phase transitions according to Berger's classification phase transitions are of two types. We have the reconstructive and we have got the displacive phase transition. In the case of the reconstructive phase transition, there is a major reorganization of the crystal structure, in which what happens, many bonds have to be broken and formed again. A reconstructive phase transition is one where you actually disrupt the parent structure and then form the new crystal structure. For example, here we have the classical example of graphite, which is in equilibrium with that of diamond. They have got very different structures. Graphite consists of hexagonal sheets, whereas the diamond contains the four coordinated carbon atoms. So, in case of graphite, we have got the hexagonal sheets, and here we have got the giant structure. This is 3D, this is 2D. Here carbon is 3 coordinated, here carbon is 4 coordinated. So, the structures are very different, and if you want to go convert from graphite to diamond, then there is a major reorganization of the structure as a whole. So, what essentially happens is that why is there a barrier to the process? There is a large barrier to the process because it involves breaking of large number of bonds and forming new bonds. So, although you can have a kinetically stable phase which can exist for a large period of time, because the barrier which is involved in converting to the thermodynamic phase is very large. So, for example, we know that diamond, which is formed at extremely high temperature and pressure, is actually a kinetic phase. It is kinetically stable. It is thermodynamically metastable, but the process of conversion of diamond to graphite does not take place so easily because of the large barrier involved. And on the other hand, graphite is the most stable form of carbon at room temperature and pressure. We see that at 25 degrees centigrade and 1 atmospheric pressure, the graphite form is the most stable form, and the diamond is the kinetic phase. So we know that there is a kinetic there is a kinetic factor here which actually does not allow for the diamond to graphite transition to take place. On the other hand, so that was about reconstructive phase transitions. Similarly, we can look at displacive phase transitions. In case of displacive phase transition, it is a distortion of the bonds only. Rather than breaking bonds, it is the distortion of the bonds only rather than breaking bonds, and the structural changes are usually very small. And this is what makes the field of phase transition very, very interesting and exciting, because in many transformations of the displacive type, there are minor rearrangements, atomic rearrangements in the crystal structure. The magnitudes of the distortions are very small. And nevertheless, one form converts in a facile way into the new phase. And also, because these are displacive phase transition, there exists a structural relationship between these forms. For example, we can consider SiO2, silica, and silica exists in different polymorphic forms like quartz, tridymite and cristobalite. So quartz, tridymite and cristallobite, these are the different polymorphs of silica, and conversion of one form into the other involves displacive phase transitions. So these involve essentially the distortions of the SiO4 tetrahedra. So tetrahedra are the building blocks in the silicates or SiO2, and first is how these tetrahedra are arranged, and then how you can actually distort these tetrahedra by making them undergo rotations. Because of the formation of this silicate chain, they can undergo distortion by rotation of the silicate tetrahedra and give you different crystal structures, different crystalline phases of silica without the necessity to break and make new bonds. Let us look at one particular figure which illustrates the displacive phase transitions. For example, we have this kind of a structure, okay, and all you need to do is you need to just rotate, and that constitutes a displacive phase transition, where you essentially now get so you have this kind of an arrangement. So all you need to do is just buckle the layers a little bit and distort some of these layers, including rotating some bonds, where you will be able to, you can rotate it along this direction, you can shear it along this direction, you can shear it along this direction, and this kind of displacive modes this kind of displacive modes will result in giving you a new structure, a new rearrangement, a rearranged structure which is having a different structure compared to the starting phase, and these are referred to as displacive phase transitions. So this constitutes the Burger's classification of phase transition and the fact that these are of two types. Now phase transitions are of different orders. We can have phase transitions which are of the first order, we can have phase transitions which are of the second order, and there is a change in the magnitude of the thermodynamic quantities when you look at these phase transitions. And now in the next lecture we will be looking at the thermodynamic classification of phase transitions, looking at first order and second order phase transitions and how you characterize these, which are very important to understand the relationship between polymers. Thank you.